this can no longer be considered part of the statement of the accident. It took a year to get the police report too, because shortly after that, the police officer who took all the notes went on vacation.
Who did they label as?
Huh?
No, ask who they labeled as at fault.
Yes, it was the other side's fault, and their home insurance covered my repair. I wasn't too concerned about that part. I was kind of concerned about the kid, not doing very well after the accident. So after I read the police report, and he basically walked away with a fractured shoulder, I was going, that was good, which is amazing. Fractured shoulder versus about $4,000 of damage on the car.
Wow.
Yeah.
He was a big guy, though.
He was a big guy. He had a lot of, let's say, buffer. Yeah.
It's very polite way to put it.
Yeah. All right, so I'll go ahead and get started. And before we get started with all the boring stuff, which you guys are all looking forward to, I'll just go ahead and tell you something that I just thought of this morning. It has to do with Ender's Game, and I'm hoping that no one has not watched or have heard of that story and do not want me to spoil the story. Okay, if you don't want me to spoil the storyline of Ender's Game, raise your hand and I won't talk about it. Okay, so everybody has either watched it or don't care. Okay, very good. Okay, so you guys know that in Ender's Game, it was a simulation at the end, and it was the actual war, right? He actually fought the war. No, I got it wrong. Okay, so I have another extension of Ender's Game. What if all the simulations are not really actual wars, but what he's doing, or what the Academy is doing, is training an AI to do it for all of us? Wouldn't that be taking the storyline one step further? Because now Ender can say, "Oh, I don't want to do this anymore. Okay, I don't like this shit anymore." So, but guess what? It doesn't matter, because now the AI can do the same thing, if not more. So if you think about it and put it back into today's timeline, okay, with all the online games that people play, especially the first-person shooter and whatnot. What if you're not actually playing another person? What if you're actually playing against an AI? And all this time, the AI is just learning from people of how to do it right. I'll try this strategy. Oh, it doesn't work very well. Okay, I'll try another strategy. Let's see how well that works. How do you know you're actually playing with another person, a 10-year-old, 15-year-old, or someone on the other side, and not a computer, not an AI that is trying to learn from you how to do it? You cannot tell, right? Well, that means that AI has passed the Turing test. Using all uppercase, with intentional spelling mistakes, and words that are censored, so you see F and then a whole bunch of asterisks and stuff like that, Yeah, so I would call that, AI haven't passed the Turing test.
I think to do that, they don't have to intentionally miss the shots. If it's an AI, they would always get headshots.
Not necessarily. I mean, because there's still reaction time to consider. Besides, the AI can usually, usually with an AI, with most games, they are predictable. So they may be perfect shots, but they always appear at the same place, or they always do the same thing. But when they learn, so what they're trying to do, is to learn from people, so they can adapt to the situation and have a variety of strategies to deploy, so it's no longer as predictable. So that's something for you guys to think about, because I think in terms of processing power, we are right at the verge of being able to do that. We are right about to be ready to do that. Yep.
Google has this thing out. They actually train their computers to play a game. They don't program them.
Mm-hmm.
It's like a computer starts randomly controlling things.
Yep.
And based on a score,
Mm-hmm.
it knows if it's winning or not.
But those are usually less complicated games, so maybe like Tetris or some other games.
Yeah, but it's not for the computer learns by itself in the beginning.
Yep.
Did you ever watch that? There's like a YouTube video of a program for an algorithm to play like simple NES games, and the program was scored about some games. It was really good at like Mario, and then when it got to Tetris, it realized that as soon as it got to the top, the game would start over and it would lose. So whenever it would build up to the top, it would just stop playing and just pause the game and not start the game back up.
That is smart. That's one way to prevent losing, right? Yep. Yep.
But it's like Watson and playing Jeopardy.
Yep.
Because even then, though, it's still based on an algorithm that has a probability of what is most accurate answer.
Yep. But that's really taking. Okay, there was another hand. Let me go. Who had? Go ahead.
You can finish this as well. Is he done or?
I'm done.
Okay. Yeah.
So like the one guy was saying it would always get headshots. Would it have access to the game mechanics, or would it just have? Like
Oh, the AI will have to do. Will only have access that you have access to, because that's the only way to truly train the AI so that it can be deployed on an Android or a robot on a vehicle, and deployed in the actual field. But that's really kind of taking the Ender's Game, storyline one step further, because it's not a person behind the actual thing. It's actually you're training the AI so the AI can do it by itself later on. So that would be kind of in a way kind of scary. All right. So let's go back and talk about all the boring stuff. Back to the boring stuff. Maybe not too boring because it has a homework assignment. Okay, so here's a resolution homework assignment. Unfortunately, I cannot schedule this to be on a New Year day because then it will be a New Year resolution. Well, but then the Earth, revolves around the sun, in a circle. So any day can be a New Year day. This can be tax New Year day, right? So
This is a New Year's resolution.
So this is a New Year resolution. I just have to do it at the same day every single year. Yep. All right. So this is your homework assignment. I want you to utilize refutation resolution, which is what we talked about last time, on conjunctive normal form, which is also something that we talked about last time, and to prove theorems. So we'll start with a few quote-unquote facts. There are only 4 variables involved in this particular system. They are P, Q, R, and S. So there are only 4 variables involved here. And the known facts of this particular system is P is equivalent to Q. You're given that P and Q are equivalent. If one is true, the other one has to be true. If one is false, the other one also has to be false. You're given that already. You're also given Q or R as an expression has to be true in this particular universe. In other words, at least one of these two has to be true. Okay? They don't have to be true both, okay, but at least one has to be true. Q is true or R is true. You are also given that it is not the case that R and S. In other words, R and S cannot be true at the same time, which is another way of saying one has to be false. Okay, at least one of these two has to be false. Are we doing okay so far? Okay, understanding the general rules that are already established for whatever reason. Okay, so there's no reason behind all of these rules other than it is for a homework assignment. The first thing you have to do is to turn all the known facts into a CNF, into a single conjunctive normal form. So we kind of talked about this already, in the previous class. And given those rules are not really nested, too badly, it shouldn't take you too much time to convert all of these into a CNF. Okay. Are there any questions about that part? How to convert a general expression into a CNF? If you convert each one into a CNF, then you can connect all the CNFs together because conjunctive normal forms can chain. You can use a format that is easy for you. In other words, when you're actually working on it, I will accept any one of the following notations. I personally like the mathematical notation, which is not necessarily your case. So I understand some people do not like it, because it takes a little bit more effort to enter and check, and it may not be your preference. So you can choose to use the C and C++ notation using the logical or, logical and the logical not operators. For those of you who really want to shorten everything and do the least amount of typing possible, this is an alternative. Okay, now this alternative is used by engineering a lot. They basically use the addition operator. When we understand the context is only in logic, the plus operator can mean disjunction. Okay, and then the multiplication, which is implied here, can mean conjunction, and then the prime means negation, but it's the negation of whatever thing is before that. So these three expressions are basically the same. P or Q and not P or S is in the mathematical format. In this case, we have the C++ format, P or Q and not P or S. But you do have to use extra parentheses, okay? Because I need to use the extra parentheses to help visually separate the individual components of a conjunction. Okay, unless it's just a one single variable, then you don't need the parentheses. And this one is the same thing. So P or Q, in this case, I'm using the plus symbol to mean it is a disjunction. And then the conjunction is the multiplication. But when we write multiplication in a normal formula, we sometimes just ignore that, right? P times Q is just PQ, and that's why you don't see any operator here because it is implied. So the last one or the third one is by far the most simplified version, okay? In terms of keystrokes and typing, that's the easiest one. And you can do it inside any editor. You can do it in Notepad, and then just copy and paste the content into the HTML editor. So that would be one of the easiest way to, as far as notation is concerned, that's one of the easiest. Are there any questions about the three formats that I can accept? Now, for those of you who really want to spell out everything, like AND, OR, and NOT, you can do that too. But I think one of these three, any one of these three will beat this fully spelled out version. All right. Any questions? Okay, so that's step one. Step one is just to convert whatever you're given with into a single CNF, a single conjunctive normal form, well-formed formula. It's a CNF WFF, yes. RTFM. Okay, step two is to prove that known facts by themselves will not lead to a contradiction already. Because if the known facts are going to lead to a contradiction, then there won't be any theorem to derive, because it's not self-consistent to begin with. So what you need to do is this is the first time you have to use the refutation resolution, and you will apply that to the CNF derived from step one. If eventually you can derive false, okay? And if you have false as a component in a CNF anywhere, then the whole thing has to be false, because it's a conjunctive normal form. So if the 0 is a component of the conjunction, then the whole conjunction has to be false, which means we have a contradiction. So if you get to a contradiction, then you can just conclude and say, oh, the rules are leading to a contradiction already, so there's no need to perform step 3. Yep.
Are you talking about something that says P and not P, or something to that effect would be a contradiction?
Through resolution, it will lead to a false. Okay, so we can go back to the slide that we looked at on Tuesday, and then just kind of take a quick look again. Okay, and this time I can do it, live, using either the notepad or mouse pad or the whiteboard. Okay, so we want to be able to do that, and not just kind of intuitively look at, oh, there's P here, there's not P here, it leads to a contradiction. We want to apply the resolution inference in order to do this. Okay. Now, on the other hand, if you apply refutation resolution, and no matter what you do, you cannot get to a contradiction, then the facts are okay by themselves, okay, because they're not leading to a contradiction all by themselves. So what you want to do is, in your resolution steps, always put the new term, whatever you are inferring, at the end of the well-formed formula in each step. For each step, indicate whatever you want to do, just make sure that I understand which two terms you combine into the new term. Okay, you can use, if you know how to do the underline, go ahead and do the underline and the double underline. If you don't know how to do that, you can always just number the expressions 1, 2, 3, 4, 5, and you can say expressions 5 and expression 10 combine into the new expression. That would be fine as well. Are there any questions about this? Okay, nothing so far. Okay. Step 3 is assuming in step 2 we are not having a self-contradictory truth system. I want you to prove or disprove this theorem. Okay, S implies P is a theorem. I don't know whether it's true or not given the 3 things that we already know. So what you need to do in this case is to reuse the cognitive normal form from step 1, and then you want to add the negated version of the theorem, which is the negation of this whole thing, to the conjunctive normal form, and make the negated theorem itself a conjunctive normal form first. Use refutation resolution to try to get to a contradiction to prove the theorem is true. Okay, you want to prove that by introducing the negation of the theorem, we end up with a contradiction. Or, on the other hand, if you try everything and you cannot get to a contradiction using the refutation resolution mechanism, then the conclusion is we cannot prove it. Okay, it is not a theorem that follows from the facts that we already know. Are we doing okay so far with what you have to do with this homework assignment? Okay, all right. And you have 1 week to work on it. It's due next Thursday, so that should be enough time. Okay. The first thing you really want to do is to perform step 1 first, okay? Because if you have any questions about step 1, you should ask that question on Tuesday at the latest. Because if you don't have the CNF done correctly from step 1, the other 2 steps, cannot work correctly either. Yep.
What do you mean by the last sentence of step 3?
Say again?
The last sentence of step 3.
Step 3?
Yeah.
Okay, let's take a look. To disprove the theorem, prove the refutation resolution cannot derive 0. So you cannot create a term 0 in the CNF.
So how do you prove that?
Aha. You can basically say that no matter how you combine the current terms in the CNF, you only end up with a term that is already in the CNF. That's basically the bottom line. Okay. That's a good question. All right, so any other questions about this? If there are no questions about this, I'm going back to the previous slide, unless the whole class decides we don't need to do that. We can just go forward to predicate calculus. If there's, otherwise I'll go back to the previous slide and just talk about refutation resolution, one more time. But this time I'll do the step-by-step. I will do it step by step, live in class. So this way it is completely slowed down and it will give you plenty of chances to ask questions. And I'm certainly hoping that most of you have read the notes after the lecture on Tuesday.
Sure. I looked at it. I didn't really fully
At least
understand
click
it.
on the link so that Moodle tells me that, yes, this link has been clicked. Okay. So let's go back to resolution. And what I'll do is I'm going to start with the inference rule itself, which is this part here. So the inference rule is saying we want to derive, we want to look for a particular pattern. Okay. So what we are looking for is something in this form. Okay. We are looking for a conjunction, where inside each term of a conjunction, there's a disjunction. Okay. Does this look like a CNF to you? It is a CNF, assuming everything inside is either a variable or a negation of a variable. So we are saying that we don't really care what is phi here. Okay, so phi can be anything. We also don't care what is rho here. Rho can be anything. What we do care is there is a psi on this side, and there's a negation of psi on the other side. So psi and not psi, is basically the non-negative form of a variable and the negative form of a variable. So all three, actually in this case, I really should not be using the Greek symbols because they're all basically variables and they're not well-formed formula. I mean, all variables are well-formed formulae too, but in this case, they're more restricted. So I'm basically saying if you can see a pattern like this, okay, then we'll go ahead and infer the following has to be true, which is just phi or rho. Whatever phi is, whatever rho is, okay? But in the process, what we have done is we started off with three variables, right? Because we had phi, psi, and rho to begin with, but we end up with only two variables, which is only phi and rho. Is that okay? Yep.
Sorry, this might be a stupid question, but what's the difference between infer and imply?
Infer is a syntactical derivation, and imply is a logical consequence.
Gotcha.
So this is an inference, which means it is just a syntactical manipulation. It has to be sound and complete. Okay, well, it has to be sound to begin with, which means if you derive a truth table of three variables, in every single case, it will imply this expression. That's a good question. Let's kind of do that step first, just to make sure that this inference rule itself is sound, okay? Because if it is not sound, everything else that we do is all pointless. So let's go ahead and do that. So we can do it by, having three more columns. Okay, so we'll do three more columns here with the three variables that are involved. As usual, we have a truth table to look at all possible combinations of zeros and ones, truth and false in this case. And then we look at each individual term and try to come up with the answer. This is only involving psi and psi, okay, the first two. So and this is a disjunction, so there will be 0, 0, 1, 1, and all ones down here. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay. Is that okay so far? Okay. This is not psi, which is the negation of the middle variable and rho. And this is still a conjunction here. So this one is everything that has a 0 for psi is going to be a true already. So we'll just kind of mark those first. So this is 1, 1. This is a 0. This is going to be a 1. And then we have, we need to line up these things a little bit better. This is going to be a 1, 1 also. That's also going to be, that's going to be a 0 and a 1. Because none of these is referring to phi, so it's just a repeating pattern. 1, 1, 0, 1, 1, 1, 0, 1, that's a repeating pattern. So once we know, each subterm of the conjunction, now we can actually perform the conjunction. So conjunction of these two is a 0. Conjunction of these two is a 0. That's a 0. That's a 1. That's a 1. That's a 1. It started not to line up already, so this is a 0, and that's also a 1. Are we still doing okay so far with this truth table? It is the one in the middle that is important because this is the entire result of the entire expression on the left-hand side of the inference. So now we need to look at the expression on the right-hand side of the inference, which is only involving rho and phi. Okay? So in this case, this is a 0. It's an OR, so this one is a 1. It's an OR. Okay, the rows are not lining up very easily for me to read. So this is a 0. That is a 1. How about this one here, the fifth one? Is that that's a 1?
The rest are all one.
Sorry?
The rest are all one.
The rest are all ones. Okay, very good. All right. So we look at these two columns, and you see that they're not exactly the same, which is actually okay. Because in order for an inference to work, okay, the semantics or the meaning only has to go in one direction. This column has to imply this column here. Okay? In other words, if this column has a 0, I don't care. So that means this one, not care. Not care, not care, and whoops, yep. That's the last one. Should have done this using a spreadsheet.
That's exactly
There we go.
what I said.
Okay, now, okay, not care either. Okay, with the rest, okay, with a 1 on the left-hand side of the inference, I need to have a 1 on the other side as a result of an inference. Is this meeting that requirement? It is. Okay, so this inference rule is okay. Okay, it is sound. Okay, it makes sense. The semantics matches the syntactical operation. All right. So once we have this inference rule, which is fairly simple, right? Okay, if you have the non-negative form of a variable on one side and the negative form of the same variable on the other side, we cancel them out, and then we just pull everything else together. But now the question is, what if phi is not a simple variable? What if this is all by itself a disjunction of something? It doesn't matter, just stick it all here. What if rho is the same thing? That doesn't matter, just stick it all here. Okay, so we are just combining two disjunctive expressions into one and getting rid of one variable at the same time. That's all we're going to do. Okay, so let's go through a few examples and see if we can do inference with those special cases. The simple cases I'm not going to talk about, but the special cases are kind of like, well, is that going to work? So we'll go ahead and talk about these few special cases. So what if we have P or, okay, which one do you prefer, as far as class is concerned? Do you want to use the mathematical symbols? Do you want to use the C++ symbols or the simplified engineering symbols?
The math.
Okay, we have math.
Just not the engineering.
Not the engineering.
Not yet.
Okay, if we can use the math one, and then we can utilize Vincent's contribution.
I actually modded it a little bit more.
Oh,
Hopefully
okay.
it makes it
Well, this is a link to your code, so it's always the recent one, as long as it's not broken. Oh, okay, nice.
So whenever you zoom, it won't take up the whole entire screen.
Uh-huh, okay, very good.
Or that input part.
Okay, so we'll go ahead and start with P or Q on one side, and we have a conjunction, and then the other side we have just not P, okay? Okay. Hey, tag, we never talked about this, okay? This does not fit the format that we were talking about. Oh, nice, I can see that. Okay, so we haven't talked about this because, hey, each side has to be a disjunctive expression by itself, and in this case, not P by itself is not a disjunctive expression. Well, we can always turn it into a disjunctive operation, operation, right? By doing what? What is the identity of disjunction? Okay. The equivalence of this question is I want x plus y as an expression all the time, okay? But somebody's giving me an expression like z, okay? So how can I turn z into an expression that involves addition?
Z plus 0.
Yep. That turns it into an addition, right? Can we do something like that with disjunction? And what would be the identity of disjunction?
False.
False, exactly, which is also 0, okay? So what we need to do is to say, hey, this is the same thing as that. So now we are happy, right? Because now we have a disjunction on one side, we have a disjunction on the other side. Everything is cool. But what is the result of this? Okay, what do we actually derive out of this?
True or false?
Okay, so this will derive, okay, and I'm going to use b dash, say derive sting 2. What do we get out of this? We get rid of p, right? Because p is both non-negating here and is negating here.
We keep
So we end up with Q or 0, right? But Q or 0 is also known as what?
Q.
Just Q. Yep, that's right. Is that okay? So that means this whole thing, by simplifying it one more step, is just Q all by itself. Because Q or 0 is just Q. And you can prove that, okay? If you want to prove Q or false is just Q, you can use a truth table to prove it. I'm not going to do it in this class. Are there any questions about this step? So if this is the case, if this is the case, what if we have P on one side and not P on the other side? That just goes to 0, right? Because we can apply the same technique twice with what we did earlier. So we can basically, the first expression is P or 0, and then the second expression is not P or 0. Then you apply the inference rule, okay? Because it's a very blind, simple syntactical manipulation. And then we end up with 0 or 0 as the end, result. 0 or 0 is just 0. So we end up with a contradiction in this case. Because anytime you end up with false, it is a contradiction. So are we doing okay so far with the basic steps of refutation inference? This is called refutation inference. No questions about this? Okay. So if there are no questions about this, we are going back to the notes that we talked about last time, which is, I think, I don't remember, what? Right here. Okay. So in this case, I have something that looks awfully similar to what we are dealing with. So basically we end up with a long CNF, okay, a longer conjunctive normal form expression that looks like this one here. Now the one in your homework assignment is not quite the same thing, but it's similar, okay, and I'll leave it up to you guys to decide, how it is similar to the one that we have been working with here. Okay. So let's go ahead and I'll go ahead and start with these three and convert each one into a CNF first. We'll start with P implies R. And I'm going to move this next to here, so this way it's easier to put them together. Okay. So we'll start with P implies R. P implies R is the original expression. P implies R by itself is not a CNF. Why is it not a CNF? Well, does it use conjunction? No. Well, that's it. Does it use disjunction? Nope. It uses implication, which is an operator that you should not have in a CNF. So we'll go ahead and do the conversion first. All right. By definition, sorry?
Isn't that not P or R?
Okay, not P or R. Okay, so let's go ahead and convert that. Not P or R, which is by definition. Is that a CNF? Not P or R is a CNF, okay? Because it is a disjunction, and in a disjunction, it only involves variables or the negation of a variable. So it is by itself a CNF already. Okay, that's good. Okay, it's good to know because now we can move on to the next expression. The next expression from here is P or Q. Okay. So P or Q is already a CNF as well. Because the objective is to convert each and every single one expression into a CNF first. And then we can chain all the CNFs together, and that becomes just a longer CNF. Okay, so this one is done. Let's look at the next one. The last one is this one here, the negation of Q and R. Okay. So we have the negation of Q and R. Is that a CNF?
Yes.
It is not a CNF. Now when I say it's not a CNF, I'm not saying this is a negation. Well, in both senses, okay? In both senses, this is not a CNF, in the sense that this is It is not true that this is a CNF in that sense, and also in the sense that this is the negation of a CNF. Is everybody catching that, what I just said? Okay, this is one of the rare cases where I actually remember what I said like 20 seconds ago, and I will be able to do it again. Okay, so it is true in both senses that this is not a CNF, in the sense that it is not true that this is a CNF, okay? It is not in the form of a CNF. Why?
It's both has a negation on the outside and a conjunction on the inside.
The negation is on the outside. What is the only thing you can apply a negation to in a CNF? A variable, exactly. And we have a conjunction expression that is being negated. So right away we know this is not in CNF format. But it is the negation of a CNF because Q and R by itself is a CNF. Okay? So the conversion from this into a CNF is to apply De Morgan's law. Okay? De Morgan's law says if you have a negation on the outside and then you have either a conjunction or a disjunction in the inside, then you can apply De Morgan's law. There are two De Morgan's law, one to apply to conjunction, one to apply to disjunction. But in this case, we just need the one that applies to conjunction. So now it becomes the negation of Q or the negation of R, like that. Now, this one is a CNF. Oops. This one is a CNF, so now we end up with 3 individual CNFs. And with CNF, the nice thing is you can chain them together. So the end result is we are now chaining all of these together, so we end up with a long CNF as follows. So we end up with something, and something, and something. And obviously I'm going to do the lazy thing. Okay, this is nice, so I can do it this way. So the first one is this guy. That's the first CNF. This is the second CNF. And this is our last, the last CNF. So now we have basically one long CNF that is the conjunction of all the smaller CNF. And this is basically representing the truth of this particular system. Okay, so all the 3 rules, all the 3 expressions that we have been talking about can now be represented by one single CNF. That's the first step. And you have to do about the same thing for your homework assignment in step 1. And the only real difference is instead of imply, we have equivalent to for the first expression. Okay, so it's a very minor change. Are there any questions at this point before we move on?
Did I break the alignment? Did I break the alignment?
The alignment.
Does it not
Even the equal to?
Yeah, isn't it supposed to?
No, you did not do anything because
okay.
I need to use the ampersand thing to make the equal.
Oh, okay.
So if I apply ampersand here, then you can see how the equal symbol is now aligning.
Let me know if I break something.
No, I don't think you can break this part.
You can't break the match X because it's just a scripting is called.
And then plus MathJax refers to the MathJax script from their side. Yep. Okay. Do we have any questions at this step? This is corresponding to step 1 of your homework assignment. Now, there's no step 2 of the homework assignment when I talked about CNF and resolution in my notes. So I'm going to do it now. Okay, I'm going to perform step 2 as if it is a part of this particular homework assignment. So step 2 is basically to look at the CNF representing the truth of this particular system and say, is this by itself a contradiction? Because if this by itself is a contradiction, there's no need to perform step 3. It's pointless to try to prove a theorem when the basis is already leading to a contradiction. Okay, so that's what we'll do. We'll try to apply refutation resolution on this particular CNF as far as we can take it. If we cannot get to 0, that means by itself it is not a contradiction, which is good because then we can move on to step 3. So So I'm going to copy and paste this. Is it okay to erase this screen?
Yes.
Okay, so we'll go ahead and just copy this part as a starting point of the next one. So we'll go ahead and erase the rest. So, and then this one, this time we start with just that one. Okay. All right, so every time you perform refutation resolution, you are looking for a particular pattern. You're looking for two sub-expressions, each one being a disjunctive expression. Each one has to have a non-negative version of a variable, and then the other one has the negative version of the same variable. We have quite a few ways to do resolution here, so you can take your pick, okay? It doesn't matter which one you pick. So we'll go ahead and just take, that to separate the lines. And let's see what that do. I think that would make sure everything is aligned, so it looks nice on the screen. Okay, so we can go ahead and pick, any two for resolution. So I can pick this one and this one here. Okay, so this one is easy because I can highlight both of them. So if I take these two and perform the resolution step, what is the result of this? R or Q. Okay, very good. So we'll go ahead and do this. So the end result of this is basically the same thing as what we had before. So this is really helpful if you have an editor, because there will be a lot of copy and pasting. We just have to say, after this we have right? R or Q. Does everybody understand why I can add that one more term, R or Q, into the CNF?
Because it's also true based on the system.
Because it's already established by the resolution step, inference. So we can keep deriving things and add to it. Okay, the next question is, does it really add any more truth to what we already understand is true in this particular system? In other words, when you look at these two steps, the first step seems to be simpler because it only involves 3 disjunctive terms. And the second step, or the second expression, is longer. It has 4 disjunctive terms. So now the question is the second form, which is this one here, is it adding any more information, or is it losing any information compared to the first one? What do you think? Is it adding or deleting anything, or is there no change? There's no change, okay? I'm just stating something that is already true, and I'm just making it more explicit. Is that okay? So you have to remember that part, because the resolution step does not add any truth. It does not remove any truth from the system. It is simply saying, oh, okay, we can actually infer or end up with this result based on what we already know. All right. So if that is the case, let's go ahead and derive the next one. Okay. The next step, we will take a look at, we combined the first two already, so it's helpful to kind of keep track of which two you have resolved already. So we can now take the second and the third one and resolve these two. So if you take the second and the third one, we can get rid of Q, so we end up with P or not R. Okay, that's the new term that we should be adding. So once again, copy and paste is going to be really helpful. So we can just say, wedge, and then we add P or not R. Okay. Are there any questions about this step? Now, when you are doing this, you have to indicate, how you got to the new step. Okay, so you can either use the single underline, double underline thing that I did, or you can just on the side say, okay, combining the first and the third expression, I get a new one like that. Okay, so either one is okay. Okay, now that we have this big mess here, there's one that we haven't really considered. We have not considered, using the first one and the last one, because they have R and not R involved. So we can now combine these two into not P or not Q. Okay, so we'll go ahead and just write it out. Just copy and paste the entire line and say, oh, by the way, we can also, state the following, which is not P or not R. And I need to change the zoom a little bit to make it fit. There we go. All right. So from 3 terms to begin with, we now end up with 1, 2, 3, 4, 5, 6 terms. Okay. So now the question is, can I combine any one of these? Can I combine any 2 of these 6 terms and end up with something that I haven't seen before? Yep. Go ahead.
What about not P or R and not P or not R?
You mean combining this one with this one here?
Yeah.
Okay, very good. Let's go ahead and combine those 2. So by combining those 2 terms, what do we end up with? Okay, so let me just highlight which 2 we are talking about. So we are talking about this one and which one again?
The one at the end.
The one at the end. You mean this one?
Yeah.
Okay, so we are canceling the R and we are leaving not P and not P on both sides, right? So not P or not P is what?
True.
No.
Wait, not P and not P or not P?
Not P, actually in this case it's not P or not P.
Not P or not P is false.
Nope. It's just not P.
Oh.
Well, nonetheless, do we have not P by itself as a term here?
No.
Okay, so you got something new. Cool. Yep. All right, so let's go ahead and add it here. Okay, so wedge, not P, all by itself. All right. Yep, go ahead.
I think we already have a contradiction. We have not P or R, and we have P or not R.
That is true. This is bad because I gave you a system that has a contradiction to begin with. but let's go there. Okay, let us go there and use it, illustrate what I mean by that. Okay, so we have a not P or R here, and then we have a P or not R. The resolution step cannot do it in one single step. Okay, so we have to do it in 2 different steps. Okay, so let's go ahead and do this. Okay, so what I'm doing here is I'm combining this step with this step here. Now you have a choice because you can cancel out the R first, or you can cancel out the P first. Okay, it is your choice, your pick. Cancel whichever one first. So we'll just say we cancel out the P term first. So if you cancel out the P term, you'll end up with R or not R. But that does not really do anything. Okay, I'll show you what I mean by that. Okay, so this is good. I'm liking this exercise here. Okay, so after we cancel out the P, we have R or not R, right? R or not R. And what do we do with R and not R?
Well, doesn't that just mean that R is
true? It's just true, exactly. Chris is right. Okay, I'm running out of space again.
If R is true, then R is
Okay. This term is simplified to true, which does not lead to a contradiction. Because it simplifies to true, which is just 1, right?
And you can add as many ones as you want to.
Exactly. Within a conjunction.
Yeah.
In a conjunction.
That's why I said
So that means we can take this term, turn it into a 1, okay, like that. But anything and 1 is just the original thing, so there's no need to even mention it. So we just kind of get rid of it.
go less.
So it was an interesting exercise, but it did not lead to a contradiction. Okay. Anything else that we can combine into something that's new that we haven't seen before? Come on, you guys can.
What about P or not R and not P?
P and not R.
No, P or not R.
P or not R, this term and the last one.
Yeah.
Okay, let's combine those 2, which ends up with just not R by itself. okay? Which is a new term. We haven't seen it before, so let's do that. So I think you guys are getting the hang of it.
You can just end up with not P, not R, and not Q. Or NQ, rather.
Well, we'll do it step by step. There we go. So very good. That is a new step. You know, not R by itself. We haven't seen before. Yep. Go ahead.
And then you can do the same thing with R or Q and not R.
You can do
Term
the
4
same
in
thing.
the last term. Make it Q by itself.
Okay. So I get what you want to say. So we are combining this one with the last one, so that we end up with just Q all by itself. Is that what you said?
Yeah.
Okay. So let's go ahead and do that. Okay, one thing you might have noticed is how would you describe this process that we have been doing at this point?
Tedious.
Tedious is one, okay.
Systematic.
Systematic. Does it require a lot of
Thinking.
creativity and thinking on your part?
NQ.
What does it actually involve? Pattern matching, right? Okay, you just try to match up. Oh, this variable is here. The negation of this variable is over here. Let's combine those two together, right? And see if there's something new. If there's something new, add it. If it's not something new, then you don't have to do anything. Okay, so at this point, can we still do anything to get new terms? Okay, now we're getting to this kind of long CNF, which has 1, 2, 3, 4, 5, 6, 7, 8, 9. It has 9 terms. It might be helpful if we have a more systematic way of looking at this, right? So what is a more systematic way of looking at this instead of just scanning it and use the eyeball algorithm to do this? Which at this point has been working really well, but it's getting slower and slower using the eyeball algorithm. So the more systematic way of doing things is, go ahead.
Is there a way we can work backwards from what we want to try to see if we can get terms in here that
No,
we can...
not really, because what we want is a conclusion of whether do we get to a contradiction, or are we going to get stuck without getting to the contradiction. Yep.
You're talking about instead of scanning, picking one term and then comparing it to each other?
Exactly, exactly. So that's what we're looking at. So it's hard for me to use the mouse pointer, so I'm just going to point it here. So we'll take the first term here and say, let's focus on the first term, and then try to combine the first term with the other terms. Okay. So we look at the first term, and then we look at the second one, and we say, hey, it is applicable, but we have done it already. Okay. So there's nothing new. There's nothing to gain here. We look at the first term. We look at the third term here. It can be done, but we have done it already too. Right? So it might be helpful to use a flag to indicate, okay, this has been combined with that term already. We look at the first term, the fourth term, they cannot be combined because they do not share a variable. One is negated and not negated on the other side. We look at the first term and the fifth term, and we say, oh, we have done this already. It basically boils down to just true, which is not doing anything to the system. We look at the first term to the next one, which is this one here. And it boils down to not P, which is already in the system already. And then we look at the first term and not P, it ends up with, we cannot apply it because not P is still, both are negated, so we cannot apply the resolution step. We look at the first one and the second last one, which is not R. We can resolve it to not P, but it's already here. And then we look at the first one and the last one. We cannot apply the resolution because they do not share variables. Okay? We are done with the first term. And then we move on to the second term and do exactly the same thing. So we look at the second term, P or Q, and then say, oh, can we combine that with the third term? Yes, we can, but we have done it already. So redoing a step is not going to add anything new, so we might don't do it. Look at the second term and the fourth term, cannot combine. Look at the second term and the fifth term, cannot combine either. Look at the second term and the sixth term, can be combined. It ends up with Q or not R. And Q or not R is not in the system yet, right? So we can add that one. Okay, so we'll go ahead and add that term. But this is the process. Okay, we just do it gradually, step by step, until we get to the point where we cannot add anything new. So we have Q or not R in this case, and I have to shrink the font one more time here just because it's getting wider. Okay. So this time it's combining Q, P or Q with which term again? I think with this one here. I cannot remember. That I think it's this one. So P or Q on one side, not P or not Q, not R on the other side. So we end up with Q or not R. Okay. But it's basically a very systematic way of trying to look at each term and see whether it can be combined with another term. Now, if I had been doing this systematically from the beginning, I would be able to actually track things a whole lot easier, because I already know, which terms I have tried to combine with which other term already, and I wouldn't be, doing this kind of randomly at this point. Okay, here's the next question. Is there a deterministic way, which means, I will know for sure that I cannot derive any additional new terms anymore? It is possible, right? Because if you look at, okay, let's say we have in the CNF, we have n terms, okay? So we look at the CNF with n disjunctive terms. So that means, if you look at this, we have n of these things, okay? If I just look at the very first item, how many ways can I combine with all the other terms? Okay. Only n minus 1, okay? So we got n minus 1 corresponding to the very first term. And then you look at the second term, how many ways can I combine it with all the other terms? Not counting the first one, because we already counted the first one the first time. Okay? So with the second term, how many ways can I combine it? N minus 2, and then the next one is n minus 3, and all the way down to
n minus n.
Well, the last one doesn't really, it's useless, right? You cannot you have to get down to only one way of doing things by the time you exhaust everything. What is the summation of all of these? If you put a summation sign over all of these, I don't even need to know the exact number. The exact number can be derived, but I don't even need to know the exact number. It is proportional to 1. Okay, I'll give you a few choices here. Log of n squared, n squared times log of n times log of n, and so on. Okay, so which one do you think is the answer? N squared. It's proportional to n squared. Okay, so after exhausting all of these terms, and I say, oh, I cannot find any new terms, then I'm done, right? Because once you try to do all the resolutions that you possibly can using the existing terms, and you cannot come up with a new term, then you're done. Because there's no point in doing it again, because there's no way to introduce new terms. Okay. Now, when I perform each resolution step, how long would it take, using the dumbest possible way? How long would it take to find out, hey, I got a term here already? How long would it take? And I have n of these things in the CNF already.
N.
Yeah, it would take n comparisons, right?
Right.
So that means, the actual complexity of the algorithm is going to be n squared times n, which is n cubed. Okay. So in the big O, or in the order of n cubed time, n being the number of sub-expressions in the CNF, I can make a conclusion, okay? Which is great, because at some point I can stop. It means at some point I can stop and say definitively and say I cannot get to a contradiction. Now, why is that important?
So it's not infinite. There's a stopping point.
Yep, there's a stopping point. So that's why refutation resolution is so useful, because if you program this in a systematic way, you cannot be running in circles. It will take time, okay? No one says this is going to be not time consuming. No one says it's going to be quick, but it will terminate. The algorithm will stop. Are there any questions about this? Which also means, it is kind of a interesting thing to give you a homework assignment, not this week, but at some point, so that you can make your own refutation resolution engine. I give you the CNF, and you guys can tell me, can you get to, a contradiction? Now I can see some faces going, no, don't do that. I don't want to go there. Well, are there any questions about this step? Are we done yet at this point? Can we derive any new terms? I think you guys got the idea, so I'm gonna stop here.
We would all appreciate that very much.
But is it helping? I mean, is it helping with, compared to the... I know the previous lecture exposed you to the concept of refutation resolution, but this is the nitty-gritty detail of doing all that stuff. Okay, but this is only to show you that the system itself is not contradictory. It doesn't prove anything else, okay? So what do you have to do to prove a theorem? In other words, in this particular notes here, I have a theorem to prove. And let's scroll all the way down to the last one. Sorry, go ahead.
We're proving that R implies Q. Is that what we're trying to prove?
The last one is this one here. So, okay, so we want to see whether this is a theorem. A theorem is basically a statement that can be derived from the axioms. Okay, what you know has to be true, you should be able to derive the theorem. Okay, so my proposal is that is my theorem. It is not the case that R implies Q. Whoops, I take it back. The theorem I want to prove is just R implies Q, but in order to prove R implies Q, you do not put R implies Q into the CNF. You put the negation of that into the CNF. And this technique is called proof by contradiction, which means if you negate the very same thing that you want to prove and you arrive to a contradiction by derivations, then you prove the theorem has to be true to begin with. Does anyone want to give me a quick example of proof by contradiction? No one. Okay, I'll give you one quick example of proof by contradiction. And it has to do with socks. My socks. Okay? And so let's say I only have one kind of socks. Okay? Because whenever I change socks, whenever I buy socks, I always buy the same kind of sock en masse. Okay? I buy like 3 dozens, 4 dozens at a time. Okay? Just so that I don't have to do anything for the next few years. So I stick all of those socks into my drawer, and every day in the morning, especially when it's the winter month, when it's dark and cold, I will reach into my drawer, not having to turn on any lights, and say, I want to get one pair of socks. All right? So the question is, what is the minimum number of socks that I have to pull out of my drawer to get at least one pair? 2 socks. 3? Well, I only got 2 feet, so I think 2 would be enough.
But you got on the 2 socks on the same for the same feet.
I only got one kind of sock.
Yeah, but like when you have 2 pairs, but you only pick 2 socks for the left foot, for example.
Oh, I don't have socks that are, I have ambidextrous socks.
But and they tie together like for the left foot and the right foot, they tie together already.
No. The socks are all loose. They're all just.
You need a strip, otherwise you can 2 socks for the same foot.
I only need to pull 2 socks to make one pair. Right?
That's for the sock for the left and the right foot.
I don't have socks that fancy. All my socks, are ambidextrous, which means they fit the left and the right. Yep. Okay, so making that assumption that all my socks can fit both left and right. Okay, so is everybody thinking that pulling 2 socks out of the drawer, any 2 socks, would make 1 pair?
Yes.
Okay, prove it. Okay, so how do you prove something that simple, right? Okay, fine. I will show you. Okay, go to the drawer. Put a whole bunch of socks in it, and say, okay, look, pull one out, pull the other one out. See, 1 pair. Now do this 20 gazillion times. Is that enough proof? No. Because what is guaranteeing the next one is going to work the same way? There's no guarantee. Okay, it is not a proof. You can only use an example to disprove something. It's called proof by counterexample. Okay, so what you do is you do a proof by contradiction. So you say, no, 2 socks is not enough to get a pair. Okay? Now, so you will say, hypothetically speaking, okay, since tech you are wrong, 2 socks is not the minimum to make 1 pair. That means, hypothetically speaking, there will be at least 1 instance where I have to pull 3 socks to make 1 pair. Is that making any sense? Okay. Now, if I'm pulling 3 socks to make 1 pair, that means the first 2 that I pull cannot be of the same kind, because otherwise it makes 1 pair already. Now, if I pull 2 socks out of my drawer and they're different, what is that doing to the whole system? What is it doing to the assumption? What is the fact that I gave you to begin with?
That they're all the same socks.
2 pairs.
Yeah, exactly. That all socks are of the same kind. So, if I have to pull 3 to make 1 pair, that means I have at least 2 kinds of socks, which is contradicting with the assumption already. And since the negation of the theorem, which is 2 is the minimum that I have to pull to make 1 pair, since the negation of that theorem leads to contradiction, that means the theorem has to be true. That's proof by contradiction. Yep.
So proof by contradiction, like, it only works if the scope of what you're trying to prove is very, very narrow, right?
No. Proof by contradiction in many cases is actually more powerful than the normal proof which is going forward. I'll give you a little preview of what is proof by contradiction. We all know this, right? Okay, P implies Q. Okay, and this is how we usually do things when we prove things in a forward manner. Okay, we just derive 1 step from the next one, from the previous one, and then the next one from the previous one, and so on. So the truth table of this, we should know this already too. 0, 0, 1, 1 for P, and then 0, 1, 0, 1 for Q. And P implies Q is true here. 1, 1, 0, 1. Okay? That's the truth table of implication as an operator. But the other way to look at this is not Q implies not P. Now, what is not P? Not Q implies not P. It's saying exactly the same thing. Okay? So if you look at not Q here, not Q is 1. Not P is 1, and not 1 implies 1 is 1. And you look at the second row, not Q is 0, or false in this case, so the end result has to be 1 here, has to be 1 here. With this one, we have not Q being 1, and not P being 0, and the result is a 0. So we can see that this expression and this expression are exactly the same. Are we still doing okay so far with this? Go ahead.
For the second line, 0, 1, 1, no, over on the left side. For P infers Q, if P is, how does that work? If P is 0 and Q is 1, and then it comes out to 1 like that?
Because if I told you if the sky is magenta, you're going to fail this class. And the sky is blue, then you can fail the class or not fail the class, and I will still be speaking the truth, right?
Okay,
so that's why when the premise is false, the conclusion can be anything. And the statement will still be true as a whole. The other way to look at this one here, I know what you're talking about, this one here, right?
Yeah.
The other way to look at this is by definition, P implies Q is not P or Q. So by negating the P in the disjunction, this is going to be true anyway because it does not depend on Q anymore. So there are two ways to look at P implies Q, and you have a false and a true. False implies true you can either look at it as not the negation of the first or the second one, or you can also look at the context and say, hey, if the first one is not true, there's nothing we can say about the conclusion. But it's the second one that we use for proof by contradiction, because by negating the conclusion, then it should also negate the premise, leading to a contradiction. Is that kind of okay so far? Okay. Oh, but what is proof by contradiction? What is P and Q in proof by contradiction? What do you put in place of Q, and what do you put in place of P in proof by contradiction?
Statement.
Q is the easy one, right? Q is the theorem. Okay, so in proof by contradiction, this is the Q itself, the non-negated version, is the theorem that I want to prove. And that's why you have to start with the negation of the theorem to begin with. But what about P in proof by contradiction?
Some theorem in the system that's known to be true.
Yep, exactly. All the axioms, all the things that we know are true already in the system in big one long conjunction, right? So P in this case, not the negated version, but just P by itself, is a CNF, or one way to do it is to use a CNF as the entire system. But the CNF for the entire system is already known to be true. So the negation of that is false. So that's why if you start with the negation of a theorem that is actually true, you should end up with a contradiction, because it leads to the negation of all the truths that you know about the system already. And that's basically the bottom line of proof by contradiction. So in the case of the sock example, Q is the conclusion of I need to pull only up to 2 socks to get 1 pair. I know the screensaver is very distracting. It's also random too. So that kind of keeps you guys guessing. If someone's time is like, oh, 10 minutes is almost up. What is going to be the next screensaver? So Q in this case is the theorem of I only need to pull 2 socks to make 1 pair. And the negation of that means I need to pull at least 3 socks to make 1 pair. P, on the other hand, is the premise, which in this case is I only have 1 kind of socks in my drawer. Is that okay? I'm kind of hoping that this will start to sink in after a while, because it is a lot to take in all at the same time, but over time I'm hoping that will start to sink in. Any other questions about the homework assignment, other than, oh man, that's going to take me a long time, unless you write a program to do it? Yep.
I just have a question about the triple equals. It's different from that at all.
Okay, the triple equal is just a more clear way to indicate equivalence. It's basically the same thing as equivalence. In other words, if not Q and R is the same thing as not Q or R because of De Morgan's law. But I use triple here because some people use equal as the equivalent operator, which is an operator that we can use in here. So that's why I use triple equal here to make it simply say this is the same as that. We can transform that into the other side. But it means the same thing as double arrow. Any other questions?
So when we're doing the proof by contradiction, we're just looking for 1 0, 1 false.
You only need 1 false in the entire conjunction. The false cannot be inside the disjunction because if you have a 0, if you have a false in the disjunction, it doesn't do anything, right? So the 0 or the false has to be by itself in the conjunction.
It has to be its own.
Right?
It has to be its own.
Yes, it has to be its own as a CNF in the big long chain of CNF. Okay. Any other questions? I'll give you guys a 2-minute head start on the homework assignment then. I'm pretty sure I have made up for those 2 minutes from previous classes too. So.
At least.
And guess what? This has been staring at me in the face the whole time,
I don't even know why
and
you bring it anymore.
Yeah,
I know.
this is so classic ADD.
Yeah.